Ever since the first studies of the Great Pyramid in Egypt have been made, researchers have been amazed at the mathematical knowledge that is encoded into the Great Pyramid, the measurements that are used in it. Even the placement of the Great Pyramid has aroused great interest among Egyptologists.
For more than 100 years, the Great Pyramid of Giza was thought to be a mystery already solved, a massive monument built by ancient Egyptians using basic tools, remarkable engineering, and the coordinated efforts of thousands of workers. But when every available archaeological record, construction measurement, and historical data set connected to Giza was analyzed by an advanced AI system without any preconceived assumptions, a different picture began to emerge. The calculations no longer aligned as neatly as expected. Certain physical marks, precision cuts, and construction features appeared difficult to reconcile with the tools traditionally believed to have been used. According to the AI's analysis, the evidence raised questions that existing explanations could not fully answer. The more data it examined, the more inconsistencies it identified between the accepted theory and the physical realities of the monument itself. What Grok AI uncovered did not necessarily overturn everything historians believe about the Great Pyramid, but it suggested that the conventional narrative may be incomplete. Rather than providing all the answers, the findings pointed to the possibility that important pieces of the puzzle are still missing, and that the true story behind one of humanity's greatest achievements may be far more complex than previously imagined. An explanation that, according to some researchers, no longer answers every question. For nearly 200 years, Egyptologists have largely agreed on how the Great Pyramid of Giza was built. The accepted view is that it was constructed around 2560 BCE during the reign of Pharaoh Khufu by a massive workforce using copper tools, wooden sledges, and carefully designed ramp systems. Over time, this explanation became so widely accepted that challenging it was often seen as stepping outside mainstream scholarship. And to be fair, the theory is supported by real evidence. Ancient inscriptions have been discovered. Worker settlements have been excavated near the Giza Plateau. Tool marks can still be seen on many of the stones, and surviving papyri describe the transportation of construction materials. For both historians and the public, the mystery appeared largely solved. Yet there has always been another side to the story. The pyramid itself contains measurements and levels of precision that continue to raise questions. Its base was leveled to within just 2.1 centimeters across a distance of roughly 230 meters. That represents a deviation of only about 0.009% from a perfectly flat plane. To put that into perspective, many modern large-scale construction projects allow variations of up to 0.1%. In other words, the builders of the Great Pyramid achieved a degree of accuracy that remains astonishing even by today's engineering standards. And that is where the debate begins. If the accepted explanation is correct, how was such extraordinary precision achieved with the tools and technology believed to have existed more than 4,500 years ago? The deeper researchers examine the structure, the more difficult that question becomes to ignore. What makes the Great Pyramid even more remarkable is that its accuracy goes far beyond what many modern construction projects require. Researchers estimate that its base exceeds common engineering tolerances by a significant margin, yet this achievement is traditionally attributed to simple tools such as wooden measuring squares, plumb lines, and water-filled trenches. The pyramid's orientation is equally astonishing. Its four sides are aligned extremely closely to true north, with only a tiny margin of error. Achieving that level of accuracy today typically involves sophisticated surveying equipment, precise astronomical measurements, and advanced positioning technology. Over the years, experimental archaeologists have tried to recreate these results using the methods believed to have been available in ancient Egypt. While many experiments have demonstrated impressive capabilities, matching the pyramid's exact precision has proven extremely difficult. The measured deviations are often noticeably greater than those found in the monument itself. Then there is the question of construction speed. Ancient sources suggest the pyramid was completed in roughly 20 years. If that timeline is accurate, it would mean that hundreds of massive stone blocks had to be quarried, transported, positioned, and fitted into place every single day. On average, that would require placing a multi-ton block every few minutes during working hours, day after day, year after year. Such calculations assume an exceptionally efficient operation with minimal delays, few accidents, and a workforce functioning at an extraordinary level of coordination. Few ancient building projects anywhere in the world appear to combine this scale, speed, and precision in a single undertaking. Supporters of the conventional explanation offer answers to each of these challenges individually. The remarkable leveling is often attributed to surveying techniques that may not have survived in the historical record. The pyramid's alignment is explained through careful observation of the stars. The pace of construction is credited to a highly organized labor force supported by a sophisticated administrative system. Yet, critics argue that these explanations are usually addressed separately rather than as parts of a single integrated process. The larger question remains: can one unified model fully explain the pyramid's precision, alignment, scale, and construction speed all at the same time, using the same technology and workforce? For decades, that question has remained a topic of debate among researchers, engineers, and historians. While the mainstream model remains widely accepted, some believe important gaps still exist between the theory and the physical realities of the monument itself. This is where artificial intelligence entered the discussion. In 2024, reports emerged of Grok AI being tasked with examining a vast collection of information related to the Giza pyramids. The data included archaeological surveys, engineering studies, astronomical measurements, geological reports, mathematical analyses, and extensive records gathered over more than a century of research. The objective was straightforward: evaluate the evidence as a whole without being committed to any particular theory and identify patterns, inconsistencies, or unanswered questions that might not be obvious when each piece of evidence is studied in isolation. What happened next would become the focus of intense discussion among those fascinated by one of humanity's greatest architectural mysteries. What emerged was not the re-examination of a single mystery or isolated anomaly. Instead, it appeared to be a broader pattern, one that connected multiple independent categories of evidence and pointed toward the same conclusion. One of the first areas that drew attention involved the mathematical relationships found within the dimensions of the Great Pyramid itself. Researchers have long noted that the ratio between the pyramid's base perimeter and its height closely approximates 2pi, the mathematical constant associated with circles. The correspondence is remarkably close, falling within a fraction of a percent of the modern value. Other measurements have also attracted interest. Certain relationships between the pyramid's height, base dimensions, and slope angle appear to reflect proportions similar to the golden ratio, often represented by the Greek letter phi. While the golden ratio was formally described much later in ancient Greek mathematics, some researchers argue that its presence may be reflected in much older structures. Viewed individually, any one of these relationships could be dismissed as coincidence. But according to the analysis, the pattern becomes more intriguing when several of them appear within the same monument. Multiple dimensional relationships seem to point toward the same mathematical constants, raising the question of whether they were intentionally incorporated into the design or emerged naturally from the construction process. The investigation then moved beyond mathematics and into geography. One of the most debated claims surrounding the Great Pyramid is that certain measurements appear to correspond to the dimensions of the Earth itself. When the pyramid's height is multiplied by 43,200, the resulting figure comes surprisingly close to the Earth's polar radius. Likewise, multiplying the pyramid's base perimeter by the same number produces a value similar to the Earth's equatorial circumference. Supporters of this theory argue that the repeated use of the same scaling factor is unlikely to be accidental. They note that 43,200 is a number that appears in various ancient numerical and astronomical systems, leading some to speculate that it may have held special significance. Critics, however, argue that such correspondences can sometimes emerge when enough numerical comparisons are made. The debate remains unresolved. Even so, the pattern raises a fascinating possibility. If these relationships were intentionally built into the monument, it would suggest that its designers possessed a far deeper understanding of mathematics, astronomy, and the Earth's dimensions than is typically credited to the ancient world. And that leads to a much larger question. Perhaps the greatest mystery is no longer simply how the Great Pyramid was constructed. The deeper mystery may be whether its builders possessed knowledge that has not yet been fully understood, and if so, where that knowledge came from in the first place. That question continues to fuel one of the most fascinating debates in archaeology, engineering, and ancient history to this day. Mathematical patterns can always be debated. Critics may argue that certain ratios and numerical relationships are the result of coincidence or selective interpretation. Numbers can often be viewed from different perspectives. Physical evidence, however, is much harder to explain away. When Grok's analysis examined records of tool marks found throughout the Great Pyramid, special attention was given to the granite components inside the structure. These included the king's chamber, the massive granite sarcophagus, and the relieving chambers located above it. All of these features were carved from granite transported from Aswan, a quarry located more than 800 kilometers south of Giza. What stood out was that some of the marks preserved in the stone did not appear to match the characteristics typically associated with known ancient tools. The challenge begins with the granite itself. Granite contains large amounts of quartz, a mineral that ranks 7 on the Mohs hardness scale, which measures a material's resistance to scratching and cutting. By comparison, copper, the primary metal available to Egyptian craftsmen during the Bronze Age, has a hardness rating of only about 2.5 to 3. From a purely mechanical standpoint, working a harder material with a much softer one presents significant difficulties. When softer tools encounter harder mineral inclusions, they tend to wander, create uneven grooves, and leave cuts with varying depths and irregular surfaces. Modern experimental archaeologists have repeatedly tested this process using copper tools and abrasive sand. Their experiments demonstrate that granite can indeed be worked using such methods, but the resulting cuts often show the kinds of irregularities that engineers would expect from the materials involved. The marks found in some parts of the Great Pyramid, however, have become the focus of ongoing debate because certain cuts appear unusually straight and consistent, even when passing through areas containing minerals of different hardness. One of the most frequently discussed examples is an artifact known as the Petri core. Recovered during investigations of the pyramid complex and studied by British engineer and archaeologist Flinders Petrie in the late 19th century, the cylindrical granite sample contains a distinctive spiral groove running along its surface. The groove is generally interpreted as evidence of tubular drilling, a technique in which a hollow drill removes a circular core from the stone. For more than a century, researchers have debated what this artifact reveals about the technology used by the pyramid builders. Some believe it demonstrates an unexpectedly high level of craftsmanship using known ancient methods. Others argue that the precision visible in the core raises questions that have yet to be fully answered. Whatever the explanation, the Petri core remains one of the most intriguing pieces of physical evidence connected to the construction of the Great Pyramid, continuing to fuel discussions about the true capabilities of the civilization that built it. When British engineer and archaeologist Flinders Petrie studied the granite core, he focused on a detail that many researchers still discuss today: the drill's feed rate, or how far the cutting tool appeared to advance into the stone with each complete rotation. Based on his measurements, Petrie concluded that the drilling process seemed surprisingly efficient. According to his calculations, the rate of penetration appeared difficult to explain using the manual drilling methods traditionally associated with ancient Egypt. More than a century later, engineer and researcher Christopher Dunn revisited the same evidence. After examining the groove patterns and cut characteristics, he argued that they resembled the results produced by highly advanced machining techniques. Among the possibilities he discussed were diamond-tipped drilling systems or technologies that use high-frequency vibrations to transfer energy directly into stone. The challenge, of course, is that no direct archaeological evidence for such technologies has ever been found in ancient Egypt. When Grok analyzed the available records, it reportedly compared these granite tool marks with a wide range of modern cutting methods, including diamond saws, rotary drilling systems, water jet technologies, and ultrasonic machining techniques. According to the analysis, some of the closest similarities appeared to come from methods more advanced than those traditionally attributed to Bronze Age craftsmen. Importantly, this does not mean modern machines were used in the construction of the pyramid. Rather, the conclusion suggested that certain marks preserved in the granite remain difficult to classify using currently accepted models of ancient Egyptian technology. In other words, the mystery is not that we know what created the marks. The mystery is that we still do not know with certainty. The tools commonly believed to have built the monument do not fully explain every feature visible in the stone. Yet, no alternative technology has ever been discovered in the archaeological record. The result is a puzzle that has remained unresolved for generations. What makes the situation even more intriguing is that these questions do not exist in isolation. For decades, researchers have treated each anomaly as a separate issue. Unusual tool marks have been discussed as technical mysteries. Mathematical relationships within the pyramid have been debated as questions of geometry and measurement. Astronomical alignments have been examined independently by historians and astronomers. Each topic has largely remained in its own category. But when all of these observations are viewed together, a different picture begins to emerge. Instead of isolated mysteries, they start to resemble pieces of a much larger puzzle, one that may require a broader explanation than any single theory has yet provided. That possibility is precisely what made the AI analysis so controversial. Rather than examining one anomaly at a time, it looked at every category of evidence simultaneously and searched for patterns connecting them all. And according to its findings, those connections may be more significant than researchers previously realized. For decades, these questions have largely been examined in isolation. Engineers focused on construction methods. Archaeologists studied tools and labor systems. Mathematicians debated geometric relationships. Astronomers analyzed alignments with the stars. Each category of evidence was typically investigated within its own field, rarely requiring every piece of the puzzle to fit together into a single, unified explanation. According to supporters of the AI analysis, that is what made Grok's approach different. Rather than treating each anomaly as a separate issue, the system evaluated them as parts of one interconnected structure. The goal was not simply to ask whether each individual claim could be explained, but whether all of them could be explained simultaneously within the same historical framework. From that perspective, the challenge becomes much larger. The conventional model must account for extraordinary leveling precision, remarkable astronomical alignment, complex geometric relationships, sophisticated stoneworking techniques, and the enormous logistical demands of constructing the monument. Each of these features may have a proposed explanation on its own, but the question is whether all of those explanations can work together as a single coherent model. Grok's analysis reportedly focused on the combined probability rather than the individual anomalies. Instead of asking, "Can this one feature be explained?" it asked, "Can all of these features be explained together by the same technological system and the same civilization at the same point in history?" That shift in perspective led to one of the most controversial conclusions of the entire investigation. The Great Pyramid does not appear to display the characteristics normally associated with a technology operating at the edge of its capabilities. In many historical construction projects, researchers can see evidence of experimentation, gradual improvement, design revisions, and lessons learned through trial and error. Precision tends to increase as experience accumulates. But proponents of this view argue that the Great Pyramid appears different. The highest levels of accuracy are not found only in the final stages of construction. They seem to be present from the very beginning, embedded in the foundation and overall design of the monument itself. There is little sign of a long learning process unfolding during the project. Instead, the structure gives the impression that its builders already knew exactly what they were doing before construction began. If that interpretation is correct, it raises a profound question. Where did that knowledge come from? This represents the most significant shift in the discussion. The debate is no longer focused on a single tool, one measurement, or one unexplained feature. Instead, it becomes a question about the source of the knowledge that made the entire project possible. According to the analysis, when all categories of evidence are considered together and forced into a single coherent framework, they seem to point toward the possibility that the knowledge behind the Great Pyramid may have been more advanced than conventional explanations typically assume. Whether that conclusion ultimately proves correct remains a matter of ongoing debate. But it is precisely this question, the origin of the knowledge behind one of humanity's most extraordinary monuments, that continues to captivate researchers, engineers, historians, and millions of people around the world. And that leads to a question that many researchers, engineers, and historians continue to debate. If the Great Pyramid reflects such an extraordinary level of knowledge and precision, where did that knowledge come from? The question is important because every major technological achievement in human history usually leaves behind a trail of development. We can see how pottery evolved from simple forms into more advanced designs. We can trace the progress of metallurgy, agriculture, and writing through countless intermediate stages spread across centuries. Each innovation leaves evidence of experimentation, mistakes, improvements, and gradual refinement. But some researchers argue that the story of the pyramids appears different. According to this perspective, the archaeological record does not clearly reveal every step that led to the remarkable precision seen at Giza. Instead, the evidence seems to show a rapid progression from earlier stone structures to one of the most sophisticated monuments ever built. The earliest large-scale stone construction in Egypt is generally considered to be the Step Pyramid at Saqqara, built during the reign of Pharaoh Djoser. It was a groundbreaking achievement for its time and marked a major leap in architectural ambition. Yet only a few generations later, the Great Pyramid of Giza appears with an astonishing level of engineering precision already in place. Its alignment, scale, geometry, and construction quality have led some observers to wonder how such capabilities advanced so quickly. Critics of the conventional timeline point out that there is no widely recognized series of large-scale experimental structures showing a gradual progression toward the exact standards achieved at Giza. They argue that the archaeological record contains relatively few examples of massive, failed attempts, transitional monuments, or projects that clearly demonstrate the learning process behind such extraordinary precision. Supporters of mainstream Egyptology respond that technological knowledge does not always survive in the archaeological record, and that much of the development may have occurred through techniques, training, and practices that left little physical evidence behind. Nevertheless, the question remains a fascinating one. If the Great Pyramid represents the culmination of centuries of accumulated knowledge, where are all the missing steps that led to it? And if those steps have not yet been found, could important pieces of the story still be waiting to be discovered beneath the sands of Egypt? For many researchers, the greatest mystery of the Great Pyramid is not a single measurement or unexplained feature, but the apparent gap in the historical record. The monument seems to appear with an extraordinary level of sophistication and precision, raising questions about how such knowledge was developed. The debate deepens with the Great Sphinx. Geologist Robert Schoch argued that erosion patterns on the Sphinx resemble long-term water weathering rather than wind and sand erosion. If correct, this could suggest parts of the monument are far older than traditionally believed. Critics disagree, pointing to alternative geological explanations, and the issue remains unresolved. What makes these questions so intriguing is that they have existed for decades. Yet they are often studied separately. Engineering, geology, mathematics, and archaeology rarely examined together as one unified puzzle. According to Grok's analysis, that is the key issue. Rather than focusing on individual anomalies, it looked at all the evidence at once. On one side are well-established facts: dynastic Egypt, worker settlements, copper tools, and organized labor. On the other are ongoing questions about precision, alignment, stoneworking, and the age of the Sphinx. The analysis does not claim to know who built the pyramids. Instead, it argues that some questions remain open and that no single explanation fully addresses every piece of evidence at the same time. The Great Pyramid still stands. Its measurements remain unchanged. The marks in the stone are still there. And after more than a century of study, the mystery continues, not because answers don't exist, but because the full story may be more complex than we currently understand.